Hello everyone. This is another video in my series on computer systems. In this one, we're going to take just a quick tour through client-server systems and clusters. This is part of Module 9 if you're kind of following along with the whole video series. And this is going to be just some topics in this module that I want you to be a little bit familiar with, but mostly it's kind of a guided reading. So if you have the book, Operating Systems, Internals and Design Principles by William Stallings, definitely worth a read through this chapter, but we're going to hit it pretty quick because I just want you to be aware of both this and a few other just different types of forms that operating systems can take for some modern applications, because it's important for us to be aware of these things. So the first thing I'd like to start with is this is a table from your book that gives you some good definitions of just terminology that we want to know. And when we're talking about a client-server system, what's the client mean? What does the server mean? And I'll be diving into this a little more deeply throughout the rest of the slides, but pause here and read through these, or if you have the book, go ahead and maybe pause the video and read through those. Make sure you're familiar with these definitions. But moving on to the client-server computing portion of this video, let's talk about what a client is. A client machine is usually just a single-user workstation that gives a user-friendly interface. Mostly we're talking about, think about your desktop or your laptop. All right? When you go to a website, for example, your browser, right, running on your system is that user-friendly interface. Your desktop or laptop is the client, and then there's a server out there somewhere running a web server like Apache or Nginx or something like that, and that's what's acting as the server. So, client-based stations generally present the graphical interface, right, including the use of Windows and a mouse, Microsoft Windows, Mac OS. These are overall operating system examples, but again, we could just be talking about a browser like Chrome or Safari or Firefox. And client-based applications are tailored for ease of use and include familiar tools like spreadsheets and things like that. The server, on the other hand, provides a set of shared services to clients. One type is a database server. We've already mentioned a web server. And what these do is enable many clients to share access to the same database or web application or whatever it happens to be. This enables the use of a high-performance system to manage the database or whatever else you happen to be managing. Whatever application has a server side, right? We can take a nice big beefy system and utilize it because we're going to have multiple clients accessing this thing all at the same time. So it gives us that centralized place, that centralized system to go to provide the services that the client consumes. A client-server configuration is different from other distributed processing, right? There's a heavy reliance on that user-friendly application, on their own system. That's so that we don't have to remotely access the server and learn a whole bunch of command line craziness, right? We want our clients to be able to or our users to sit at their client systems and be able to easily consume our services. And that really helps, especially if it's the kind of service that you end up paying for, or it's an interface to something like your banking or your shopping. We want it to be easy for people. That's going to bring people in and have them using our platform. Now, this illustration shows us how clients and servers can work together, right? Even though they might be in different hardware on different operating systems, because remember, these are two completely separate computers. They can be anywhere in the world. They don't need to be near each other or hooked up by an actual wire, nothing like that. This can be your computer sitting at home and, Google's web server out there somewhere. Who knows? Now, what we've got on the client, and we'll just take things from the top down on these, we have our presentation services, right? That's that user interface that we want to make sure we have on the client workstation to kind of make things pretty and easy for our users. Then we've got our application logic. Now we've got the application logic will basically be broken up into two parts. We'll have the parts of the application logic that run on the client, and we'll have the parts that run on the server. And the client will just actually make requests of the server, which will then respond to those requests. So this can be through an API or something along those lines. So the network application, because of course this is going to be reliant on network communication, has those two portions. We got the client portion and the server portion, so the entire application lives in two different places at the same time. So we've got the application that talks back and forth between the two parts of it to do things on the server, get information from the server, and actually run jobs on the server sometimes, and then display that to the user at the client workstation. We have communication software. Now, this also works together. This is our protocol interaction. This is where we do the networking. A prime example is TCP/IP. Right? This is how we coordinate, how we talk back and forth to get those requests from the client to the server and the responses from the server back to the client. Now, after that, when we get to the operating systems and hardware platforms, those can be completely different, right? The client can be running Windows, the server can be running Unix, right? They can be on very, very different hardware platforms, and that's our benefit, right? We can actually use our kind of just normal, not horrifyingly expensive laptop or desktop to access the server-side resources, which can be a whole lot larger and more powerful to do what we need to do with our application. Our next illustration adds a database application, right? This adds a database into the mix. And so if we've got a database application where we're just running the database from the server, and the client can actually have the application logic living completely on the client, like you see here. We've still got our presentation services at the top. The application logic lives at the client, and it's the database logic that interacts with the server by making those requests and responses. Our protocol interaction is the same, except on the server, we're going to have a database management system as well, and then the database can live either on that server or in a completely separate server that's just dedicated to the database. All right, so we're just kind of expanding things, and we still have different operating systems, different hardware platforms for both of our pieces of this application. So something that we want to be able to do with a client-server database is basically narrow things down. We want to be able to keep things reasonable, right? So if I've got a database with 1 million records on it, we're probably going to do a few different queries to narrow stuff down to get the client what it actually needs. So it might put in a somewhat general initial query that might give you 100,000 possible records, and we'll kind of present that, just let them know, hey, there's 100,000 possible records. We're not going to return all of those. We're not going to send all that data over the network. We're just going to let the client know, hey, your query has given you 100,000 possible results. The client can then do another query that narrows those down, maybe to 1,000. And then a final query, which finally gets us the individual record that we actually want. And it can be more than one, but still, the final query is when we finally get the records that we're actually interested in. And those are the only records we're actually going to send over the network from the server to the client. If we, misusing this would be if we just sent a query and then sent, 300,000 records that meet that first query. It's like, no, we don't want to do that because we're sending a whole lot of extra information. That's a security problem, right? We don't want to send data that we don't have to send. And we're also putting a lot of the computational load onto the client because then the client is still going to have to query through that a few times to get to the records that they're actually interested in. So said, let's do what we saw on the last slide, where we have the server doing the processing and just reporting, hey, I got this many records, I have this many records, I have this, and keep paring it down until we only return the records that the client is actually interested in. Now, when we talk about client-server applications, we have 4 general classes. These are host-based processing, server-based processing, cooperative processing, or client-based processing. And these just basically tell us how much is done on either the client and or the server, right? How much of the computational load is on the client versus on the server. So let's take a quick look at all 4 of these classes and just get an idea of the differences. So in host-based processing, we're not actually talking about true client-server computing, right? This is the kind of thing that you used to see in traditional mainframe environments, and usually the user interface would just be a dumb terminal. It's not actually doing anything. It's just giving you a terminal emulation or of some sort to the server. So everything, including the presentation logic, all the presentation logic, all the application logic, the database management, would all be running on the server. So again, that's not truly a client-server architecture, because again, the client is just acting as a simple interface to the server. Now, in server-based processing, we do have an actual client-server setup, and we just move the presentation logic over to the client. So the client is still actually doing something. The server doesn't have to worry about presenting an interface to the client anymore, but it's going to run the entire application, all the database logic, and all the database management. With cooperative processing, we've now got to what we saw in that first figure we went through a few slides ago, where we split the application logic between the client and the server. Right? So the server has its piece of application logic, the client has its piece, and those will communicate back and forth with each other through those requests and responses. Finally, in client-based processing, we have all of the presentation logic and all of the application logic running on the client. The only thing that's going to be split is the database logic. So the database logic will still have to have two separate pieces, one for the client, one for the server. The database management system, of course, will still run completely on the server, but it's that database piece that's going to make requests and responses. The presentation and application logic is all going to run just on the client without an actual server component to those pieces. Now, another thing to keep in mind is that we don't have to just have this be two systems, right? We can have multiple systems involved in this whole approach. So this is an example of a three-tier client-server architecture where we have our client, where just as usual, and then when we have a middle-tier server, this is the application server. So this would run the application logic, and then we can have back-end servers that act as our database servers. So we don't have to restrict this. A client-server setup does not have to be restricted to just two computers. We can expand that architecture to multiple tiers, still be in a client-server scenario. We can just expand the support and the number of systems we have backing up the server side of that application. Now, to really make client-server approaches nice, we should have a set of tools that provide uniform means and style of access to resources across any platforms that we happen to be using. Right? We don't want things to be different or have to have different versions of things for different operating systems, for example. And this is where something called middleware comes in. It enables programmers to build applications that look and feel the same, right? Same methods to access data regardless of location of that data, same kinds of interfaces regardless of what operating system is being used at the client. And the way we can do that is to use standard programming interfaces and protocols that are between the application and communication software and the operating system. So probably easiest to understand that by looking at it in an illustration here as we've been looking at it before. So what we can have is on the client, we have our presentation services, our application logic, and then it's middleware that runs on both the client and the server that provides the interaction between the two systems. Then after that, everything is pretty much the same, right? We've got our communication software, so our underlying network protocols and communication protocols can happen. We run our application services on the server, but it's that middleware that talks to each other, and that gives us a nice, consistent interface, programmatically speaking, to go back and forth between the server and the client pieces. So we can have our application running up at the top level, and then there's APIs that run to interact with the middleware, right? The middleware runs in its own piece at its own level. There are platform interfaces that allow the operating system on whatever hardware you're running to talk to the middleware. The middleware then talks to the application through APIs. So that gives us a way to keep things consistent and make things a lot simpler as well as far as updating and changing things. So let's talk for a second about how we're going to do those requests and responses, right? When the client and server talk to each other, we've been keeping it kind of general and meta so far. Let's talk about how that actually happens. And by and large, that's going to be through something called remote procedure calls. This allows programs on different machines to interact with a simple procedure call and return semantic, right? So this is what we'll use to access remote services. This is a widely accepted and very common way to encapsulate communications in a distributed system, right? The communication code can be generated automatically. The client server modules can be moved among computers and operating systems with, very little modification or recoding. That's because we standardize these remote procedure calls. So that makes it easier for us, again, just like middleware, that makes it easier for us to update things, keep things consistent for our users. Now, when we deal with remote procedure calls, there's a couple terms that we want to make sure we're aware of. Those are blocking versus non-blocking. And we've seen these before if you've looked at the other videos in the series. In a non-blocking approach, a process is not suspended as a result of issuing a send or receive. It's efficient and flexible use of message passing facility by the processes. It's difficult to test and debug programs that use these primitives. And with blocking, we use what are called synchronous primitives. Send doesn't return control to the sending process until the message has been transmitted or until the message has been sent and acknowledged received. Receive doesn't return control until the message has been placed in the allocated buffer. We also want to think in terms of persistent binding or non-persistent binding. And what we're talking about there is when we make a logical connection and how we manage that logical connection. In non-persistent binding, we basically just make a logical connection, prepare to exchange commands, and with non-persistent binding, as soon as we finish up the individual remote procedure call that we decided to make, as soon as those values are returned, the connection will get dismantled. So if we're going to be making lots and lots and lots of remote procedure calls between a single client and server, we probably don't want to use non-persistent binding, right? We've got overhead in creating and then dismantling those connections. So why would we do that every time if we're going to be making a ton of different remote procedure calls? The other option is persistent binding. So we set up a connection that's sustained after the procedure returns, right? And then that same connection can be used for future RPCs. If a specified period of time passes with no activity, then we can terminate it. And again, this is for something that makes repeated calls to remote procedures. Well, it makes sense for us to maintain that connection as long as we're making those calls and we've got traffic on it. And then, of course, the timeout means, all right, once we've stopped using it for a while and we're not, actually making tons of calls, at least at the moment, we can tear that down and create a new one if we start making calls again. Now, another concept to keep in mind is synchronous versus asynchronous RPCs. This kind of comes down to the blocking. In synchronous RPC, it's basically going to act just like a subroutine call, right? It's got predictable behavior because it's going to block. It's going to wait until it gets back the response before it moves on. But what it doesn't do is take advantage of the distributed computing that we might be able to take advantage of otherwise, and that's where we can use asynchronous RPC. What that does is just doesn't block the caller, right? Where replies can get received when they're needed, right? So we can actually make procedure calls and keep on running. We can keep on allowing the client to execute locally in parallel with the server invocation until it gets the remote procedure call response when it gets it. Now, before we dive into clusters, let's talk for just a second about a little bit of a challenge that we have to meet when we're using these kinds of distributed computing, and that's file cache consistency. When we use a file server, the performance of file I/O can degrade relative to local file access, of course, because we're sending this stuff over the network. We no longer just have to get it from the disk into our system. We have to get it from the disk and then load it up and send it across the network and receive all that. So what we can do is have file caches that hold recently accessed file records, and because of the principle of locality. Remember that from way back in our earlier modules? The same principle of locality that we talked about with program caches work the same way, right? It works exactly the same way. Use of a local file cache can reduce the number of remote server accesses that we have to make. And the simplest approach to the consistency is to use file locking techniques to prevent simultaneous access to a file by more than one client. So we can grab a file, lock it on the server, do what we need to do on the client, and then write that back to the main file storage area, right? So we can use caches for files in distributed systems just like we use them for memory. So moving on to clusters. Now, while we're still talking about distributed computing, clusters are very different from a simple client-server kind of situation. What we're talking about with a cluster is a group of interconnected whole computers working together as a unified computing resource that can create the illusion of being one machine. And a whole computer, in that definition, just means a system that could run on its own apart from the cluster. Right, so we can add these to clusters and take them away as much as we like. And each of those whole computers that go into a cluster to form the whole cluster is referred to as a node. Now, clusters have some pretty big benefits. We have absolute scalability, right? We can have dozens, hundreds of machines, each of which is a multiprocessor. We have what's called incremental scalability. Which is we can configure clusters in such a way that it's possible to add new systems to the cluster in small increments. Right? So I can start out with a cluster that's got 100 systems, and then I can, over time, just add more and more and more whole computers to make my cluster more and more powerful. They have high availability because the failure of a single node isn't critical to the system. Right? It's just because one of these computers within a cluster fails, that's okay. I've got a whole bunch more, right, that can kind of take up the load and keep things available. And you tend to have superior price per performance, right? The price to performance ratio tends to be pretty good because we can use commodity building blocks, right? It's possible to get a cluster put together at a lower cost than a single large machine because I can just buy cheap systems to act as my nodes. It might take some more of them, but we can usually get some pretty good pricing to add a bunch of power to our clusters. Now, we have some operating system design issues when we deal with clusters, right, such as failure management. And we could take two approaches to deal with failures. We can have highly available clusters, right, that offers a high probability that all resources will be in service. Any lost query, if it's retried, will be serviced by a different computer in the cluster, right? So this is what we do if a node fails, right? If we lose a query because of a node failure, we'll just try it on a different node, right? We'll get that thing done no matter what. The cluster operating system doesn't make a guarantee about the state of partially executed transactions, and if a failure occurs, the queries and the progress are lost, okay? So that's one thing. If we lose the queries, though, remember, we can go back and run them on different nodes. We also have fault-tolerant clusters. This is achieved by the use of redundant shared disks and mechanisms for backing out uncommitted transactions and committing completed transactions. So this ensures that all resources are always available, right? So it gives us a little more safety, but we still have to go through some overhead as far as having a method of tracking those queries and doing a committed transactions versus uncommitted transactions kind of approach. That takes a little more administrative overhead. So the function of switching an application and data resources over from a failed system to an alternative system in the cluster is referred to as fallover. Okay, so if I've got a node that has certain application and data resources that fails, and I'm going to switch it on over to an alternative node, that's what we call fallover. Now, when we restore applications and data to the original system, once we fix it, that's referred to as fallback, right? So if I've got a node and it starts having issues and it goes down, the fallover is where we move the application and data resources over from that to another node to cover for it. Then I can go pull the node, I can fix that computer or even replace it, pop that node back into my cluster, and then when we restore the application and data resources to that fixed node, that's fallback. Now that can be automated, but it's only desirable if the problem's truly fixed and unlikely to recur. Right? So if I've got a node that's having periodic problems and overheating and shutting down and stuff, I might not want to fall back. I might want to pull that thing completely, right? So I don't necessarily want to automate fallback, because then subsequently failed resources can kind of bounce back and forth between computers, and that gives us performance and recovery problems. So we want to be a little careful about what we automate and what we kind of keep control of ourselves. We also have to have effective capability for balancing the load among the available computers. It doesn't make a lot of sense for me to have 1,000 computers in a cluster and be using the first 200 at 100% of their capacity, and the rest of them are sitting idly, right? Let's balance this out and get better performance from everything. So this includes that requirement that the cluster be incrementally scalable. I want to be able to add new nodes as I need to balance out the load, right? Again, I don't want to add a bunch of new nodes and have them not doing anything. Let's balance out the computational load. Now, in some cases, to use a cluster effectively, we want to end up executing software from a single application in parallel. And there's a few different ways we can go about making that happen. We can use a parallelizing compiler, right? So this determines at compile time which parts of the application can be executed in parallel, and then split those off and assign them to different systems in the cluster. We can use parallelized applications, where the programmer actually writes the application right from the start to be effective when running in parallel and to be run on clusters. Now, that places a high burden on the programmer, but it might be the best approach for actually exploiting clusters. So, if you're doing something that is going to have a very high level of available parallelization, and this is going to be run on a big distributed system like a big cluster with a bunch of nodes, you might actually be better off just writing that thing to take advantage of parallelization right off the get-go. We finally have something called parametric computing. This can be used if the essence of the application is an algorithm or program that must be executed by a large number of times, each time with a different set of starting conditions, right? So at that point, we're not necessarily parallelizing it. What we're doing is saying, okay, let's have a whole bunch of different instances of this application with different parameters or different input sets, and we'll just run them all at the same time. So we're not parallelizing the algorithm itself. We're just sending the application out and having it run independently on a whole bunch of different nodes with the appropriate different parameters and inputs.